Stefano Foffa is coming from Geneva University, and I will not tell you his curriculum is, as I don't remember it exactly. And he will talk about well, something that I believe is terribly interesting and is related to the recent discovery of gravitational detection of the gravitational waves and which are the measurement and how to do them. Thank you very much.
Hi, thank you everybody for attending. I got a lot of things to say, so I really will start right away from the outline. And that is composed of two introductory sections. That is a general, really short introduction about gravitational waves, about the sources and the most important sources, which is the binaries, coalescence. There will be a little bit about data analysis, just to put some firm ground on the part which we follow, which is the supposedly interesting part, which is in which I will discuss the detection of the first two gravitational wave events in LIGO, and also how they can extract the parameters, that is the physical parameters about the masses of these black holes, the spins, and so on. And then we conclude just speaking about the future, what we expect for the next few years of operation of these interferometers. So, okay, let's get it started. Really, the basic, I will not spend much time on that. What is a gravitational wave? It's a perturbation of the gravitational field, which is a metric, which tells us how to measure distance. And basically, we can do perturbation theory around flat space-time, Minkowski, for our purposes. Actually, we should do also perturbation theory around the cosmological setting, because the sources we are measuring are far away, but nothing changes. Basically, qualitatively, we can just follow this path. And so if we just insert this perturbation here, a fixed metric Minkowski plus this ripple, which is a gravitational wave, we found in the Einstein equation, a wave equation, sourced by the stress tensor of whatever source is around. And the first order, if we extract from this equation the lowest order expansion in terms of the velocity of the sources, we get the famous quadrupole formula that tells you which a varying quadrupole generates a gravitational wave. And once this is generated, when you go outside the source very far away, this term is zero, and you get a box H when you equals zero. It's a wave equation, so we have these ripples of space-time propagating like a wave. And how do we see these waves? They manifest themselves as changement in distances between free-falling particles. Okay? We have here a circle of particles which are in empty space, steady with respect to one to the other. When the wave passes, the distance between the particles changes with this pattern, so it is squeezed in one direction and make it longer in another direction. And we have two possible directions of squeezing, which correspond to the two polarizations of a gravitational wave, which are inclined one with respect to the other by 45 degrees because the wave is a spin. That's it. Okay, the most important source of gravitational wave is binaries. It's a binary system. The two stars or black holes orbit around each other. That makes a variation of the quadrupole of the system. So the system emits gravitational waves. So energy is lost by the system. The orbit shrinks very, very slowly, but eventually shrinks, and eventually the two stars or the two black holes collide. That is, the collision is actually what has been measured by LIGO a few months ago. But before going into the details of the measurement, we had to know that we already have indirect proofs of the emission of gravitational waves by these systems in a phase where they are still far away from collision. Okay? For example, the R-stellar pulsar, it's a binary system in which one of the two stars is a pulsar. Okay? A pulsar means that it emits electromagnetic jets, very powerful, and one of the jets is intersecting our line of sight from time to time. Okay? So basically, we have two stars They orbit around each other with a period of 8 hours, so they're pretty close, but not close enough to collide for the moment. They will collide in 200 million years. But and one of the two stars is a clock, because it emits regular pulses and we can measure them. And by measuring these pulses and the Doppler shift and the delay times of these pulses, we can measure the orbit with very good precision, and we can follow this orbit, which has been followed for decades here. And from here, we can measure the shrinking of the orbital period. And it has been measured for years, and it is in perfect agreement with the prediction of general relativity if you take into account the emission of gravitational waves, and thus the loss of energy causes that orbit to shrink. Okay? I would like to underline that this line here is not a fit to a point. This line is an independent prediction, and the point just on top of that. Okay? So this is just for introduction. Now let's wait this system for 100 million years, and let's wait until the orbital period is not 8 hours, but it's a few seconds or milliseconds. So we are arriving at the final stage of the life of the system when they coalesce. And the gravitational wave signal, which is emitted by the system, has a peculiar feature, which is depicted here, which has several distinct phases and features. In the first part, it is basically when the stars are still spiraling, so they emit a almost sinusoidal gravitational wave pattern, and this is a part which we can calculate better. Basically, we do perturbation theory, and the perturbation parameter is basically the speed of the stars, which can reach up to 0.1 of the speed of light. Still, 0.1 is still rather small, and we can do perturbation theory. And actually, this it's an expansion really in V over C, and we also see that this E over C for a self-gravitated system for the Wheeler theorem is related to these are the parameter, which is the curvature of space-time around the system. Okay, so we are actually expanding in two parameters which are related, which are one. Okay, and this is called the post-Newtonian expansion. So when I say NPN, it is this order in perturbation theory. So what we do is just take the Gaussian equation and we go up and up and up to 4 for the moment, up to 8. I mean, 4 PN means 8 power of V in this expansion. There are several techniques to do that. You can work at 11 of the equation of motion, or of a Lagrangian, or you can use the Hamiltonian approach. Both have some advantages or drawbacks, but in the end, this is what we do, and we have some control of this phase up to some point where the speed is so high that we just cannot trust our perturbation theory. And at that point, we use numeric simulation, full general relativity numerical simulation, which can follow this, can describe this very really violent phase of the signal, that is the coalescence. Okay? So we have this amplitude of gravitational waves which increases. The frequency also increases because the period is shortening. At some point there is a plunge, which gives a big burst. And eventually you are left with one single black hole, which is radiating away all the imperfections, the non-circularities. And this is the last part of the life of the system. Okay, until at the end there will be just one black hole spinning eventually, and that's it. I will focus for most of the talk on this part, because this is a part I know better, and this is a part where we have most analytical knowledge. While on this part we rely on numerics, so our knowledge is less codable, gives less information in terms of the parameters of the system.
Is all the numerics just based on bog standard general relativity, or do you get other models used?
For the moment, research is done assuming general relativity is the theory. There are other searches where we look for deviations, but the starting point for looking for the signal is that. And it is important to have a very precise waveform, because if you don't know what you're looking for, the signal is so small that you're never going to get it. Just in passing by, I will mention that there are other sources of gravitational waves. They're not being detected yet, but the research is going on also for these sources. And it is, I'm mentioning them because it shows us that this signal is a kind of a mixture in terms of features between two kinds of signals. On one side, we have a periodic pattern, like the first part of the spiraling, which is provided, for example, by rotating neutron stars. If you take a perfectly spherical neutron star and make it rotate, the quadrupole is not changing, so it will not emit gravitational waves. But neutron stars are not perfectly spherical. There are little mountains, a few centimeters high, and that is enough to generate gravitational waves. You see the amplitude is very small, 10 to minus 24. Normally, for this event, we have 10 to minus 21. That is the relative displacement of the 2 points of a circle when the wave passes by.
Is it to scale that previous diagram? Is the relative amplitude at the end really only slightly more than...
It depends on the masses of the system, but it might be. Yeah, I will show you the real signal.
Read about the amount of energy which gets thrown out. It's very concentrated right at the end. And from there,
yes.
It's not obvious that that would be the case.
It might not be obvious, it depends on the masses of the system.
Sure.
Yes.
Thank you.
So this kind of signal is, you see, it's very small, but it's periodic, and it can last for an indefinite amount of time. The star can rotate for quite a long time, more than the experiment length search. So even if it is small, you have a lot of time to look for it, and so you can have hope to get it. And more or less, you know exactly what it is. It's a sinusoid. On the other end of a spectrum of possibilities, there is this supernova explosion, which is just very violent, very big in amplitude, I wouldn't say, but 10 to minus 1 is large in this work, this business. But you don't know anything about that. So it's difficult to search, even if it is loud, because you don't know what to look for. I will not mention a stochastic, and yeah, just to tell you that this coalescence signal has a bit of both. A part which is low amplitude, very, very well modeled, another part which is a burst, which more or less you know what's going on, but not quite.
So when you say 10 to the minus 21 or so, what are units?
The unit is a random unit because it's the relative variation of the length of the two circles. Okay. So we have to measure this number like that L over L, 10 to minus 21. The better thing to do is to use an interferometer to make it big. And rather than a Michelson, you use a Fabry-Perot. That means that the laser area, the light is going back and forth, which means that in some sense you have an effective length of your interferometer which is larger than the physical length. So you have here, normally you have 4 kilometer arms, but the effective part of light here is much larger, like hundreds of kilometers. Okay? It wouldn't make much sense to make something larger, first of all for cost reason, but most of all because if you make it larger, you become larger than the wavelength of the gravitational wave you want to measure. And then you wouldn't, the effect would not sum up because if you have several wavelengths inside your interferometer, you have cancellation. So this is more or less the optimal length for this for the same frequency band we are looking for. It is between 10 and 1,000 Hz. Okay, everything is done at the top of available technology and even further, but still you can imagine that 10 to minus 21 on 4 kilometers means less than the size of the nucleus. So first of all, that sounds crazy, but we have to take into account that you're not actually measuring this length to this precision. You are measuring, first of all, the variation of the difference of these two arms with the precision. Moreover, you're not tracking any single atom of the mirror with the precision, but what you're measuring is more or less a collective motion of the mirror. So you're kind of averaging over all the atoms on the surface of the mirror that makes a huge number. So that helps explaining how can you reach this figure. So basically, in practice, what is done is to create an interference and adjust the mirrors in such a way that there is no signal coming in without any external disturbances. So you don't know what is this length, but when a disturbance, eventually gravitational wave passes, there is a variation here and some power comes in, and that's how you make the measurement. Okay? Still, 10 to the minus 121 is a very small number, and the real signal that you want to catch is buried inside, below the noise of this object. So to extract the signal, we need to do a match filtering, okay, which is a very important technique, which is crucial to make the detection, and basically consists of knowing exactly what you're looking for, basically this waveform, okay, and this waveform varies if you change the masses of the constituents. So you have to make one trial for every possible value of the masses and of the spins of your binary system. Okay, so, but let's pick one, for example. You know exactly what you're looking for, and you multiply it by your output, by the output here of your interferometer. The output is made of two parts, the noise, supposedly large, and this signal, supposedly small. So if a signal is present in this product, you have a part which is basically stochastic. It's a random walk because this noise here is just stochastic. And when you integrate, it grows like the square of the integration time. On the other end, this little part becomes h squared. There is no stochastic part, and so this integral grows like t. So if you have enough time, this part may win over this, and you could get the signal popping out of the noise. Okay? And that also explains why, if you have a long signal, you can hope to detect it even if the amplitude is small, because the time is working. Okay? So the lesson that we draw from this reasoning is that we have to know very well what you're looking for. We have to model very well the waveform that is created by these late stages of the coalescence. And in particular, what we need to know very accurately is the phase of a signal. And the reason is the following. Suppose that I am looking for the signal, and I do a match filtering with the template which is not accurate and goes off by half a period of oscillation at the end here. That means that when I do the integral, in the first half of, suppose let's say I go off by one period. In the first half of the integral, the real signal and the fake signal I injected in the data to do the search are in phase. So the integral is a positive contribution and everything sums up. At some point I go out of phase, so when I have a peak here, I have a negative peak in my template, and so the integral starts getting negative contribution, and I lose completely the information. Okay? So I have to know the phase with a precision such that I don't get off phase never during this iteration time. On the other hand, if I just have a template which is missing the amplitude by a few percent, who cares? This peak will be a little bit higher or lower, but still I wouldn't miss, any information won't be erased. Okay? So I need to know this waveform with a good precision, and especially in the phase part. Okay? And okay, this I will skip that. Just to tell you, I'm quantifying how much well I should know the phase, and in the end, the result is that I'm in the PN parameter expansion, which I was mentioning before. The minimum requirement is that I have to go to 3 PN. That is 6 power of V over C. Okay. So, okay, this is my last slide. It's a bit heavy, but it's the last one before I go to the discovery, and it is necessary to understand how all the parameters are estimated from the signal. So I'm writing here basically the phase of gravitational waves in terms of some parameters which I will explain now. So basically, this is the output of my detector. It is, I told you that a gravitational wave has two polarization, and I have one output, so I'm basically taking a linear combination of the two polarization, and the coefficients of this linear combination are just a geometrical factor, which just depend on the incidence inclination of a wave with respect to the interferometer. Okay, it's a geometrical factor. Okay, the two polarizations are made of three parts. So we have the oscillating part, which contains the phase, which I discussed below, an intrinsic part, which I again discuss in a minute, and then another geometrical factor, which is now related to the source. So this I, this iota, is basically the inclination of the orbital plane of the source, again with respect to the line of sight. Okay? So in the overall amplitude, here you have one geometrical factor here, one geometrical factor here, an oscillating part, and an intrinsic amplitude. The intrinsic amplitude is made of 1 over r factor, as every spherical wave, the distance, and this particular combination of masses, I call MC, is called the Church mass. Basically, it is basically the total mass times the reduced mass to the 3 over 5. It is what it is. It comes out of calculations. Okay. So what you measure best when you look for this kind of signal is the Church mass, this particular combination of masses. Okay. And then here I just built a time using the dimensionful constants which we had position, and this is the time of coalescence, and this is the time where you are recording the data, and basically there is a negative power, so this tells us that the behavior of the amplitude is that it grows. Okay, as long as t approaches Tc, this becomes larger. Eventually it would explode, but it is then that the Poisson-Daniel approximation breaks down, and then you will have to resort to the numerical. Okay, but the trend is this one. Okay. To finish this slide, the phase. Again, the first factor of the phase contains this Church mass, which is really the most important quantity you can fix. And then there are corrections. 1 pn correction, v squared over c squared. 1.5 pn correction, which contains terms of all the v cube over c cube, and all the corrections, which will be computed up to 3.5 pn. Okay, which is I made this partial because here it's just to tell you that I need to know all these terms to make the detection. And here for the amplitude, actually I don't need to go very far in the expansion because it's less important. Okay, this nu is this part here. So if you are able to measure the first part and the second part, you know MC, you know nu, which is another combination of the masses, and then you can hope to resolve for the individual masses of the system. And finally, here, this is where the spin of the two stars start to enter the game. It enter at 1.5 pm. Via this particular combination, and so on. You can forget this purple part. It is just made just to take into account of the fact that since the sources are very far away, hundreds of megaparsecs, actually you should take into account that there is a cosmological expansion during the arrival time. So we do not only measure the real masses of the stars, we measure the redshifted masses of the signal. But there is a way to correct for that in order to, if you know the redshift of the source, you can correct for that. But in any case, for the sources which have been detected so far, this correction is negligible. It's very small, not negligible, but it's very small. It doesn't affect the reasoning which I'm putting forward now. So, okay, here we can start looking. Yes.
Go back for a second. You have one signal.
Yes.
And something in the region of 10 to 20 parameters, and you are not fitting them.
I am not fitting them, no.
So you have this huge parameter space.
Yes.
And we...
No, the parameter space is not that big. You have two masses for the search.
Well,
two masses.
Eta, phi, iota.
No, that goes, it's all degenerate. That goes in 1 over all amplitude. Okay, you will not resolve these parameters individually, but they will just make one amplitude. Okay.
Okay. So mainly the idea is that you mimic each of those, and then they can play along.
Yes, it can be closer and better oriented or farther well oriented. Yes, and at the moment it's not, with the data quality we have, you cannot resolve that more than to some extent. I will come to this later. So let's go to the detection. At some point early this year, the community became famous. We made the press because finally we have detection of the first gravitational wave signal. So in that case, it was the detection of a coalescence of two black holes, each of which had a mass of 30 solar masses. And it was a big deal, and for some reason, because in one event you had the first gravitational wave detection, the first direct observation of heavy black holes of such masses. Some slightly lighter black holes have been observed in the X-ray binaries, but this observation is more, let's say, systematic, model dependent. But well, this was really almost a direct observation. And in that event, not only one black hole was seen, but three black holes at the same time in a particular moment of their life. It was two black holes colliding and generating a third one. So it was really an event which doesn't happen very often. And the fourth, we had for the first time the evidence of existence of intermediate mass black holes. We know that black holes of order of 5 solar masses exist, because they must exist for stellar evolution. We know there are giant black holes in the center of the galaxies, rich galaxies, but the mass range 100, 1,000 was about a bit terra incognita, and we're just seeing the birth of one life. Then later on, another event was seen. This type of coalescence was a little bit less spectacular, two smaller black holes, and that was another event recorded in life. Let me discuss a bit. Let me show just the signal as they are. This is a filtered signal. Okay. This is not the output of LIGO. The output of LIGO is a lot of noise covering all of this. But after you have made the match filtering, what comes out is this. Okay? There are two interferometers, and these are the two signals seen by the two interferometers. And this is the retroconstruction of what is supposed to be the real signal if we didn't have the residual noise of the interferometer. And that is also an interesting. We show that in the frequency and time plane, and this is a distinct feature of a coalescence in which the frequency and the amplitude of the signal are increasing both with time. This is really the chip, the spiraling, and then the coalescence. For the other event, I chose to show another kind of graph, the whole reconstructed signal. You see it has a much longer in spirally phase with respect to this other. And it lasts much longer. This is 1 second, and this is 200 milliseconds. Okay. The reason is the following: these black holes are much larger. LIGO is sensitive only starting from 1/10 Hz on. Okay, so we start seeing stuff when the orbital frequency is 10 Hz. Okay. But these black holes are much larger, so it means that they collide before, when the orbit separation is still large, because they're just that big that they touch each other before. And so they enter in the frequency band of sensitivity of LIGO, and soon after they just collide. And so we see just the last, you can see barely 8 oscillations that correspond to 4 orbital periods. These two are much smaller black holes, so they can go closer to each other, and so they collide at a larger frequency, and we see those cycles. On the other hand, maybe you can see that, yes, the amplitude here is larger, because there is more mass going on here, and here the amplitude is smaller, but it's compensated by the fact that the signals last longer. Okay? So how do they make sure that what we are seeing is a coalescence and not whatever noise which can come in this instrument? First of all, there are data quality checks. Then on every detector, you just build this quantity, which is basically the signal to noise ratio. And then you make a cut and you accept only events which have a signal to noise ratio up to larger than 5.5, for example. In my SNR 5.5, if a noise were Gaussian, would be a big deal. But the noise of this instrument is not Gaussian. There are large queues on the largest SNR part. There are glitches everywhere. It's a highly nonlinear machine. And moreover, you have to take into account that there is a tire factor due to the fact that I'm trying a matching filtering for every basically point in a parameter space. Okay, and basically the template bank is 250,000 possible waveforms, so that makes a huge tire factor. And in the end, even if you accept SNR larger than 5, you get a trigger every few seconds. Okay, and then there is also quality data and consistency data which I am not talking about. So what do you do when you have a trigger every few seconds? Well, this is why you build two detectors instead of one. When you go, you look to the other detector, and you require it at a trigger for the same template in the same parameter space within a time which is compatible with the light travel time between the two detectors. Okay, and that reduces enormously this amount, and in the end you are left with a handful of candidate events which you have to validate. Okay. So okay, you have these candidate events, and you have to make sure that they are not just by chance two pieces of noise happening by chance with the same feature at the same time in both detectors. That might happen. There is a probability that this can happen. So how do you estimate that this is not just an accidental coincidence? There is a trick. You have to generate. Your experiment lasts 3 months. That is, the first round of data taking was lasting 3 months, and with 3 months of data, you don't have enough statistic to estimate the rate of accidental coincidences. But you use a trick. You have your two data streams of the two detectors. You shift one of them by 1/10 of a second, which is a time which is larger than the lifetime travel between the two. So now you have this shift data and the other data stream, and you make again the coincidence like if it were you do the true job. Now, any coincidence you find there, it's accidental. It cannot be of any real origin. And you do repeat the game by doing many shifts, 1/10 with 1/10 of a second pace, and you generate an incredibly large amount of equivalent noise detector. And then, basically, for 3 months, you can generate 6 million years of equivalent noise. And then you make your statistics. Okay? So, you have this signal to noise ratio, you have this coincidence, you have an estimation of the noise, and now you build your statistic. Okay, first you correct your signal to noise ratio just by some quality factor check, which ensures you that you don't have that excludes the more evident case of glitches. Then you square the two noise factors, the two signal to noise ratio of a single detector, of every single detector, and you sum them in quadrature, and you will get something which is basically the combined signal to noise ratio. Okay. For the event, the first event, this number was 23. Okay. You have an event which has an overall signal to noise ratio of 23. And now you ask yourself, how many events this loud I got in my 6 million years of noisy data? And the answer is 0. Okay? And that brings you to conclude, assuming a Poissonian distribution of this kind of accidental coincidences, that for this event you have an upper bound of the false alarm rate, which is one event every 2 million years. Okay? So if you have operated the experiment for 2 million years, you would have one accidental coincidence that loud. Okay, and that is the main piece of evidence that brings you to the conclusion that this is a real event. Okay, the force of rate is ridiculously slow. And this is depicted in this graph. This is the loudness of the event, and this is how many events that loud you expect in the duration time of your experiment, which was 3 months. So here the number is 0 because you didn't have anything. So you get this is an event. Now, once you have validated this is an event, you take it out of a stream data stream and you redo a shift. Because now you know that it was not noise, and you have to generate a new 6 million years of noise without that event, because it was a real thing. Of course, if you have a loud real event and you make a correlation with whatever it was in the other detector, you might have a chance of getting something, because you had a loud event on one side and whatever you get on the other side, maybe you do something. That explains this long queue here. But once you have validated the event, you have to sort out the event, redo the whole shift thing, and the new noise floor is this one. Then you go and look at the second loudest event, it was this one, and again, that was a combined signal-to-noise ratio of 13. How many events did I found in the new 6 million year data stream of that amplitude? 0. Okay, and again, so that is a validation of a second event. There is a third event here, and both are equivalent if you have to measure in terms of Gaussian standard deviation. They are both 5 sigma discoveries, okay, in terms of probability. Okay. So we are pretty sure that we are. There is a third event, which is a kind of borderline. That is the rate of having an accidental coincidence of that loudness is 1 every 2 years, and you have 3 months of data. So is it a real gravitational wave or not? For the sake of detection, you say no. You are not on the safe side. It is basically 2 sigma limit, so you don't consider it as a candidate. But still, I mean, it is there. It is at 90% a gravitational wave, but you don't claim it because you want to be on the safe side. Okay, so we are left with these 2 events, and now I'm going to, that was the part of the detection, now I'm going to discuss the parameter estimation. Do you have a question?
Can I ask
Yes.
a very basic question? Is it right, did I tell you this, that one of these events has been identified as being a known pulsar? Is that what you said?
There was some work on that, but it has been not validated.
Which leads me to, I mean, what, do we have any idea which direction these things are in?
The direction is very pool constrained, and I will show you. For the reason which I was mentioning before, which actually is clear here. No, here. The right direction is here, and it's all the regenerate to make with these geometrical factors and with the real amplitude to make just one amplitude. So it's really degenerate with other parameters, it's difficult to constrain. We have only one information about the other direction. It is the time delay between the observational in the 2 interferometers. And given the time delay, you can draw a circle in the sky. That is the region where it can come from, but it's a circle in the sky, and it's a fixed circle, so it's not a thing. So, okay.
Can I ask you something?
Yes, see.
In this raw definition, you have a no maximization process, in the sense that are you matching towards some fixed database of signal, or once you are close, so rho I is large, you scan around or you generate new,
Exactly.
trying to match. So there is a
We do that.
maximization process.
Yes, but for the detection, this is what you do. You have your grid or in parameter space, which is calculated in order not to miss too much. And once you detect the signal, of course, you go and look at it more closely. So I'm now discussing parameter estimation, and the 2 events with respect have some differences, which is of some importance. The first event had a few cycles visible, we just discussed that. The second event had a long inspirance phase. And in general, both events are pretty high in the parameter space of masses, which are studied here. Okay, this is basically every point is a template which is being tested to make a detection, and you see this is the first event at the extreme. It's really an extreme case, and this is the second event, still high masses. Okay.
So you have no templates in there.
No, okay, the picture is not good, but there are templates, they are very sparse.
Okay.
Very sparse, not because you don't expect them, because you will be already in trouble if this density of point would be equal to the expected rate of events. This is not the case. This density of points in the template bank is related to the accuracy you need to resolve to detect the event. As I was saying before, low masses, a lot of cycles, you need to know the phase accurately, very accurately, because there are many cycles, and so you need, if you miss the mass by a little bit, you are going to miss the event. So you need a lot of points here, and you need less points there, okay? Still, it is true that in the landscape of a parameter space, this point is really extreme, and this also is a bit tight, okay? And it has a consequences of the parameter estimation. It is the part which we know go better, the spiraling part, which is dominated by our analytical knowledge, is less important relatively to the violent collision. Okay? In particular, for this event, the signature ratio is equally divided. Half of it is accumulated during the spiral, and half of it is accumulated in the plunge. Here there are a bit more for the spiral, but I mean, with a bit of luck you could do better. If you detect a neutron star, you attend to the 4 cycles and you get a good measure.
What do the boundaries mean physically?
The boundary here is just because you take one mass larger than the other. Here is that if you take a black hole which is too large, an object will fall in it before reaching 1 Earth of orbital period, so you're not going to see that. Okay, and so remind this slide, the phase with shared mass here. So I told you that the phase is the most sensitive parameter. This is the first parameter you find in the determination of the phase, and that is you expect to be the parameter you measure better in your system. And indeed, okay, forget this part because it is related to what I was saying before between the detector frame and the subframe due to the cosmological expansion. Let's focus on this here. In any case, the difference is not, there is basically no difference here because the redshift is small. The chief mass is the second line here. It is measured to 6% accuracy in the first event and 3% accuracy in the second event, which makes sense. The second event had more cycles. Okay? The total mass of a system, that is something which is well measured by the fit with the numerical part. When you see the plunge, it basically is dependent on the total mass and a few other things, but basically it's dominated by the total mass. So that first event, loud event, had a good precision on the total mass, while the other is less precise, because the event is less violent, and the SNR is more on this spiral part than in the plunge. Now, if you have two combinations of the mass, in principle, you could resolve individual masses, but in principle, but since there are errors here, doesn't work very well. You might find another combination of a mass, which is the mass ratio here, which is hidden here. First order in post-Newtonian expansion of a phase, you find this mass ratio, basically. So that's another combination of masses, which is poorly resolved in both cases. And you put all of them together, and you can deduce the values of the two masses individually. And so there is a conflict between here a good determination of the chirp mass, bad determination of the total mass. In the end, this is what matters, and the better determination of individual masses is in the loud short event, rather than in the little bit less loud and longer event. That is the determination of individual masses. And the final mass is known with the same precision because it's basically determined clearly the final mass is determined by the plunge. We don't know, in the post-Newtonian part, we don't know anything about the final mass. And there is another quantity which is interesting, is the radiated energy. Okay? It basically depends on the total mass, and is known to that precision in both cases. Okay? This is due to it's due to the numerical simulation show us that whenever you have two black holes of some size colliding, you radiate that quantity in energy. And you see, it's 3 solar masses radiated in a few milliseconds. The luminosity of this system at peak is larger than the luminosity of all the stars of the universe combined in that moment. Okay. Now, let's go to spins. Spins enter in our parameter estimation first here, 1.5 pn of the expansion of the phase. That is a combination of a component of spins parallel orthogonal to the orbital plane. Okay? So SZ, if you want. And then there are other combinations we enter later on in higher post-Newtonian expansion. But it could enter in principle also in another way, which is a bit trickier. If you have a spin component which is non-orthogonal to the orbital plane, which is a bit off, then we will have precession. If you have precession, the spins will precede, and since the total angular momentum of the system must be conserved, also the orbital plane will oscillate, will precede as well. And then that could manifest itself in, since the orbital plane is here, in a modulation of the amplitude. Okay? So system in which the spin precedes can have a modulation of the amplitude. It was not the case for the two systems, for the two events that we measured, and that's why the spins of the constituents are poorly constrained. Basically, we don't know just the order of magnitude of that. Okay? Because they are very high masses. The post-Newtonian expansion is not very well, so you cannot extract a lot of information from this part. And there was no precession, so the spin are basically unknown, just upper bounds. On the other hand, the final spin is very well known. And the reason is that the final spin, that is the spin of a final black hole, is the total angular momentum of the system, and is dominated by the orbital angular momentum of the stars. Since we know more or less the orbital part with some precision, basically this is why we can now measure the final spin of the. And in both cases, they are pretty fast. This number is basically, there is a limit for the spin of a black hole, and normalizing to that limit, we are at 0.7, more or less. Okay? They are spinning pretty fast. In agreement with expectation from astrophysical reason, which was not a surprise. And finally, the distance, I use here the luminosity distance because this is literally what you measure, is known with very poor precision, 40%. The distance is around 400 megaparsec for both events. And, well, the reason is what I discussed before. There is a lot of degeneracy. You measure only this overall amplitude. You have a bit of a hint where it could come from the time delay of the arrival between the two detectors. Then you also know the energy radiated. So in principle, if you know the energy radiated, you could build a relation between the distance and the intrinsic amplitude you measure here. So you put all things together, and it poorly constrains the posterior distribution for the luminosity distance. Some additional information here, just here you see the other direction. You would have a circle, but if you put together all the other marginal information, you can break this circle. This is somewhere in the southern hemisphere. This is for the first event. And also you have a little bit of information about the orbital plane of the orbit of the two stars. It seems to be anti-aligned with line of sight, but it's not really well constrained. This is a graph which shows that with the luminosity distance. Okay. So, okay.
Can I just add, so
Yes.
I mean, the parameters that characterize black holes is mass, spin, but it's also charge.
Black holes are neutral. Astrophysical black holes are neutral to all purposes.
Yeah?
Yeah.
Is there any reason why that's true?
Well, charge is a very strong force, and so basically it gets neutralized by swallowing matter. No, but charge black hole are theorist things that do not exist in our astrophysical space. Okay, let me just a couple of minutes. I just mentioned that there have been tests on. I mean, general relativity is assumed in all this process to generate a place to check the consistency of to assess quality data statements and to do any kind of check. But after you have made the detection, you can go on, look at your signal closer and see if there are any deviations. I will just mention this one about the gravitational mass. Basically, you have this signal, and if you have if this signal contains many frequencies, as you can see, if you have a mass of the graviton, graviton of different frequencies will travel at a different speed. And since we are far away, at some point we wouldn't observe the signal, we would observe a distortion. And by limiting the distortion, we can set a limit to the mass of the graviton here. Now there is also the issue of polarization. You see, the signal emitted by the binary system has two polarizations, and we measure just one because we have one interferometer, and the interferometer measures just one difference between the arms. Actually, we have two, but they have been built in order to be parallel and to measure the same. So this factor is actually the same for the two interferometers. This was done on purpose because we wanted to maximize the probability of coincidence. Because you need two detectors to do the discovery. On the other hand, if you do that, you lose the possibility of having an orthogonal combination that to give you information about the polarization. So polarization, we don't know whether this is consistent with general relativity. It is left for future developments. Let me skip this, and there is another test I want to mention. Once you have your event, you can insert a nuisance parameter in each of the positive expansion of the phase and fit it and see whether it is compatible with 0 or not. And this is the result. This compares the first loud event, is the coefficient of this kind of this phase. The nuisance parameter, I mean the deviation from GR of each coefficient of the phase for the loud event, and this is compared with a double pulsar, like the kind of which led to the indirect discovery. And so, okay, the first coefficient is better for the pulsar, which is observed far away from detection, because you've been observing it for 20 years. You collected a lot of data, and so it's better. But this pulsar has a speed which is very low, while this system has been detected with speed which are pretty high. So it is not surprising that as you go high in the post-Newtonian expansion, the limits of the coalescence start to beat all the previous limit. But you still see that I put here 1 plus, and the error is the upper bound is 1. So it's not a big constraining or general relativity, okay? And the reason is that basically, first of all, this event was very loud, was very short, and the post-Newtonian approximation was not good. And you see here that now I combined the two events. This is the first, and this was the second. And you see that the second one does better than the first because the post-Newtonian approximation varies better because you have more cycles. Okay? But there is another reason for which you don't get exceptional limits, is that there is a degeneracy. You could have a little bit a parameter, a deviation from GR here, compensated by just a different value of a physical parameter. Okay? So if you have few events, you don't have much statistics to get. When you really detect routinely hundreds of events, then you can start do some statistics and beat these bounds very easily. And so I am about to conclude. There are two certain directional improvement of after the detection has been made. The first is that we get other events which are different from the two I showed before. Maybe one with more cycles that would end up us to have better positional expansion and to have more precision in this parameter determination. And also for this kind of arguments of GR test. And also we could be more lucky and see some preceding binaries which will give us some information on the spin. On the other hand, more detectors are becoming operational. Virgo will join the two LIGOs this fall to start a new science run, so we will have 3 detectors. And of course, 3 detectors means a lowest SNR threshold. So with 3 detectors, clearly that one, if Virgo would have seen that one too, that would have been claimed as detection. So you have more events, and clearly more statistics, more possibility of detecting different kind of binaries. You have more precision of another direction because you have a 2 LIGO in America, and then you have a time delay of another third detector in Italy that gives you 2 times delay, basically 2 independent times delay, but to better constrain the arrival direction. If you constrain the arrival direction, you break in the degeneracy in the overall amplitude, so you can better determine the distance, the amplitude, the orientation, and so on. And finally, polarization. The third detector is not oriented at the other 2, so you could measure an independent combination of polarization and study also that one. And just as last slide, the situation of the detector network is the following. So Virgo is joining in this fall, and there will be several runs. In 2016, this run, which is called O2, will last a few months. There will be again maintenance to improve the sensitivity. There will be another run over here, then again maintenance. And these are the expected sensitivities at each stage, which are expected to reach the design sensitivity by 2020, something like that. Okay? This, by contrast, was the sensitivity of a run of the old LIGO a few years ago. It was the sensitivity of that run where the detections were made, and this is the goal. Okay? By 2020, another 4 detector will join. It's a Japanese detector under construction right now in a mine, so it's underground, which is better to beat seismic noise and so on. It will be also cryogenic, and it's very cold, so also the noise related to laser or whatever will be very, very reduced. So by 2020 we will have 4 detectors, and the 5th will join sometime, somewhere, at some time in India. It has been formally approved, not yet, the construction has not been yet started, but it has been formally approved. So at some point we will have a 5th. There is no detector in the southern hemisphere, but it's not a big deal. For astronomy with light, you need something in the south, because you're blind. For gravitational waves, they go across the Earth, so you don't really care. Okay? And what is really important for a network is that the detectors are very well spaced. And 2 in the US, 1 in India, 1 in Japan, 1 in Italy, it's not better. Okay, so the future is bright, and we expect hundreds or, let's say, tens of hundreds of events in the next 10 years. That's it.
Okay, questions? Please.
What is the physical wavelength of the measured gravitational waves?
The physical wavelength is okay. You have let's say 100 hertz. That means 3,000 kilometers. Yes.
related because you gave this bound on the graviton mass, and it was from a particle physics point of view, and it's a bound on the
quantum wavelength, which is basically h of bar of n.
Yeah.
It's a way of expressing it.
yeah, Schnurfeld. So I'll do the calculation
Yeah.
for the mass. And
Yeah, sorry, yes, you're right. It's pretty low.
it's expected. So if the graviton is massless, it would be infinite.
Yeah, exactly. So let's upper bound. And it is clearly better than the measurement of the impedance classified by 400 miles.
Other question.
How do you estimate how many events might be seen?
How do you estimate how?
Yeah, I mean, you're saying there might be hundreds of events, but I mean, what's the basis for that expectation?
No, that's what we see.
Yeah.
That's what is seen. I mean, if you just before. No, my last claim.
Yes.
Okay, well, there are a few tricks. First of all, you measure the change in sensitivity. If you gain a factor of 3 in sensitivity, you gain a factor of 3 in distance. That is a factor of 30 in volume. I tell you already something. Then you know that you have instead of having 2 detectors, you have 3. You more or less can estimate.
At the moment, you don't know how far events are apart, do you? At the moment, you don't know how far the events you've received. You've only got 2 or 3 events, so you don't know the spacing between the events. So
yes, of course. I more or less know that there will be 2 events in 3 months at a distance of 400 megaparsec. So if I say I can see a volume 30 times larger, I expect more or less 30 times more events. It might be off, but more or less maybe. And moreover, you have a third detector, so you can estimate that you can make the accidentals flow go down, so you can accept events with the lowest noise ratio because you have detectors.
So how far are you sensitive at the moment, distance-wise, do you think?
Well, you see basically 1 gigaparsec. It depends also on the orientation. More or less 1 gigaparsec. You see that event I showed you, the first detection was the best you could see in terms of masses, and it was 400 megaparsecs. Maybe it could have been better oriented, but more or less this is 1 gigaparsec.
This technique, the technique of the matching technique, is that used anywhere else?
Yeah, absolutely. Everywhere from any lab, yes, it's an old technique. It's really used. I used in my lab because to detect what was that. Well, no, it's not. It's
but basically you've got a database of
possible waveforms.
functions.
Yes.
So
Yes.
how many did you say?
250,000. They cover all the space. So you have so many that you are more or less sure you don't miss any.
And how many? And these functions, one such function, how many parameters does it involve? A single function.
4. There are the 2 masses, and you take for the detection, you take only spins on the z-axis. So 2 masses and 2 sz. That is not optimal because spin could be not aligned, but test has been done and you don't mix that much. While covering the whole space would be a nightmare and even difficult to compute. So the detection you do that. Once you have done the detection, you do a nice search and then you allow the spin to go everywhere.
What about the detector that is going to be sent in the space?
It has not been approved yet. There will be, I think, another decision for the next one. The ESA priorities next year. It is around. It is 15 years in the future since I was finishing my PhD. and it is still 15 years in the future.
It's just
I hope it will be
translational
done
invalid.
because it will be really exploring another kind of particle space. So it will be very important. But for the moment, we can just hope it will be found. But not before 2030. By the time it is found, they will build and send.
Are these measurements in any way sensitive to dark matter? Dark matter in on a specific way, in some sense. I mean, should there be a large content of dark matter? Could it could generate gravitational waves? And could you have any idea about dark matter detection here in direct?
I don't think it will affect the in that frequency range. I have to expect. Rather than astrophysical.
There's a theory paper on the archive today claiming there are effects, some birefringence effects or something.
Okay.
Caused by, but of course, these must be tiny effects compared to
But,
the signal.
I mean, will be loud enough?
I don't think so.
Because I mean, I also used in my youth year study string cosmological models for forecasting background cosmological origin, but not to be seen.
I just spoiled it accidentally
Yeah,
because it had
yeah.
gravitational waves and the tiny. Oh, that fits.
I mean, a normal lambda CDM model with normal conduct matter is not supposed to do. And if you want to go to something else,
Okay. Any other question?
Over what time scale do you do your matching? When you match, you don't know where you match over. Not over 3 months.
Mm-hmm.
What you have your functions which are matching.
Okay. No,
Over
the signal lasts a few seconds.
You don't know where the signal is.
Hmm?
You don't know where the signal is.
Okay, the signal can last from 15 minutes to a few seconds.
Okay, over that.
That's more or less the length scale of the matching you do. 15 minutes will be Newton star, low mass. They will coalesce at kilohertz, so you see many cycles. And for the black hole hole, you just saw it less than a second.
How long did the analysis take? About half a year, wasn't it?
Not really. Well, the first event was so loud it could almost be seen through the noise. And so they collected 15 days of data just to have the statistics, and they rushed the paper, and in 2 months it was out. And for the other one, they finished the 3 months data, and then they have also quick detection system for loud events to, in the case a supernova explodes, they can send information to telescopes and to point there, but it didn't happen at the time. In principle, it can be done.
Okay, if no other question, let's thank Stefano again.